So hello, friends of the sun. Welcome to the Starkly Speaking reading group. So my name is Anton, and I'm going to substitute for Hannes today. And it's a pleasure to have Andrew Campbell today and to know about his most recent research. So Andrew, correct me if I'm wrong. So Andrew is an AI research scientist at Zyra Therapeutics, and you may know Andrew for his pioneering research in discrete diffusion and flow models, particularly for protein sequence generation. So I'm very excited to see Andrew's presentation, and the floor is yours.
Thank you. Yeah, thank you for the introduction. Yeah, so I'm going to talk about this paper, Self-Speculative Mass Diffusions, that I did an internship at DeepMind with Arno, Valentin, and Jashin. So I guess I'll go over a little bit of like the background for discrete diffusion, just as like everybody's on the same page. We have this like say we're generating this sentence of text. You start this like generative process where you have many different tokens, all starting in this like masked value, and then like as you proceed through the generation trajectory, you like gradually unmask some of the tokens, where each like row in this diagram is say representing like one generation step in the generative trajectory, and then at each step you kind of reveal some number of tokens, switching them from like a masked value to like a real value until you've kind of generated the entire final sentence that you're trying to make. So I guess one issue with mass diffusion sampling is that, you know, it can take a lot of steps in that generation trajectory to generate your final data point. So if we want to be able to generate text quickly, then we need to be able to reveal more tokens in one step than like the standard approaches. So, you know, ideally, if we have this kind of intermediate state with these four masked variables, it would be great if we would be able to like reveal all of those masked variables in one go and then get to like our final clean sentence. So like the more tokens you can reveal in one step of your generation trajectory, the faster you can sample. So like the problem is that normally we have we have some model that is having a distribution over these masked positions that's like telling us, you know, what's it predicting those token values to be. And this predicted distribution of the masked positions is usually factorized. So when you sample new token values for those masked positions, you get prediction that is drawn from a factorized distribution. So factorized here meaning that like in each of these masked positions, the token that you're drawing from it is like independent of the tokens that you're going to draw in the other positions. So like say we're trying to infill these three masked tokens here, one sample from this factorized distribution could be like the quick blue fox swam over the lazy frog. And then another sample could be like the brown fish jumped over the lazy frog. So you can see like when you're trying to fill in all of these tokens at the same time from a factorized distribution, you can have these like inconsistencies in the sentence because the infilled values, they're not like consistent with each other because they're independent and they can't see what the other values are that you're drawing for those masked positions. So like ideally we'd have blue fish swam or brown fox jumped to make sure that like those values that you've revealed are consistent with each other. So
And so
yeah.
here you mean that you do a single forward pass through the model, right? And then you like sample it.
Mm-hmm.
Yeah.
Yeah. So that one step corresponding to like one forward pass. So like writing out this problem, like this factorized distribution problem, if we have this like numbering of the tokens in this sentence, and we're trying to predict the values in the positions 3, 4, 5, and 8, because those are the ones that are masked, then like this factorized distribution, you can write it as some distribution over x, 3, 4, 5, and 8, given like the revealed context 1, 2, 6, 7, 9 in the other positions. And then that like factorizes into this set of 4 distributions over, you know, each of those masked positions, and they're all like given the same context and they're all like kind of independent of each other. So yeah, what we would ideally like is this non-factorized predictive distribution where you can sample like all of those tokens from those masked positions at the same time and have them be like internally consistent with each other. So like you get the fish and you get swam, you get fox and jumped, you get the right colors like to go with all of these token values. And then the way that that looks mathematically is, you have this predicted distribution over positions 3, 4, 5, and 8, but it doesn't factorize. It's not splitting into that like set of 4 factors with the same conditioning information, because you now have like this non-factorized predictive distribution. So if you were to use like standard techniques to try and sample from a non-factorized distribution, you might use some like autoregressive style of approach where like, say you want to sample the 3rd token first, you sample that with the standard context, and then you like take your sampled X3 token, you add it into the context, and then you sample like X4 and then X5 and X8. You have this like growing context. It's like basically just how you sample like language models, autoregressive models. But then whenever you like increase the context, you have to do another forward pass of your neural network, because you've increased the context, so it has to like recompute weights and everything. So it's like, you've lost all the benefits of like trying to generate multiple tokens at the same time, because in order to like make this big jump, you have to use many forward passes. So you're like negating any efficiency gains. So like the solution we're using in this paper is speculative sampling, which is a way to sample from these like non-factorized distributions, but in like very few numbers of like forward passes. So it's like a schematic of what speculative sampling looks like. You have this kind of current context, which is like your currently revealed tokens. And then you have this draft model that generates you this draft sequence, like this long chunk of text. And then you take this long chunk of text and you put it into this target model, with the target model defining your kind of non-factorized distribution. And then you get given the probabilities that are coming out of your target model, you accept some number of those drafted tokens from the draft model. And I guess the key thing is like, it has to be cheap to create this draft sequence. Like your draft model can't be this expensive autoregressive model that you have to sample many times to get the draft. It should be like this fast, maybe small, but maybe not. Some fast model though, that gets this like draft sequence. And then this target model is usually like an autoregressive model that you can take a full clean piece of text, pass it through all in parallel, and get probabilities over all of those sampled positions in one forward pass. Like, I guess the key thing is like an autoregressive model, you have to sample it. You have to do many forward passes to sample it as you have this growing context. But if you just have a full clean sentence, it's only one forward pass to assign probabilities to every token in that sequence.
And so sorry for interrupting. Just to clarify, so you start with this context, so which is like a sentence with some let's say words masked, and then you do a single forward pass through some cheap model, right? So through also just a single forward pass through this draft model,
Yeah.
and then you get all the candidates, or like this speculative sample, and then you just run a single forward pass through the target model just to get the probabilities, and then you just accept like until the first until the first word is high enough probability, right?
Yeah. So you have this like specific algorithm to decide like what tokens to accept from that draft sequence, such that the output of this whole process is some tokens that are distributed according to the target model, as if you had just sampled the target model like as normal. So it's like you get, you calculate your draft probabilities on your draft tokens, calculate the target probabilities on those tokens. You compute this acceptance probability as this like ratio of target probabilities to draft probabilities, and then with this acceptance probability, you either accept this current token in the sequence, or you reject it and resample from this adjusted distribution. So it's like you kind of have this sequence of draft tokens. I'm gonna check the first token of the draft, the second token of the draft, third token, and so on. And then for each, one in that sequence, you kind of roll the dice on the acceptance probability. You either accept it, or at some point you'll, reject, and then you will resample that token, and then that's it. So you get a bunch of accepts, one reject, and then that's the end of the speculative procedure. And then you have some number of tokens, and you can prove that like the joint distribution of all of those tokens together is distributed according to the target distribution. And this is just like from some 2023 LLM papers who came up with this.
And so then, like after you exit this for loop, you just repeat it again, right? You just you again do it like a single forward pass through the draft model and then repeat it.
Yeah, exactly. And so it's like, for one forward pass, you get multiple tokens rather than just one token, as you would if you weren't using speculative sampling. Yeah. So I guess in the title we have this like self-speculation kind of idea. So I guess in this schematic we have these two models, like one draft and one target. And what the idea of like self-speculative sampling is that you're using some subset of a model as the draft, and then you use the full model as a target. And the draft is actually like, it's like the same model, but you're just using different layers of it. So in this 2024 paper on self-speculative decoding in language models, they have these like transformer layers. So they have 4 layers in this diagram. They only use the first 2 layers to define some draft distribution that's fast to sample because you only have to go through 2 layers. You generate some draft using 2 layers, and then once you have a draft sequence, you pass it through all the layers, and you can reuse some of the activations that you had in the causal in the drafting stage, because if you like track the computation parts, they're actually like unchanged between drafting and verification. So you can kind of reuse some computation there, you add some extra computation with these further layers, and that gives you like this more powerful target distribution that you're sampling from using like the drafting of the early layers. Yes, so I think it's now possible to like give you a high level view of what this paper is doing here. Is we're taking these kind of self-speculation ideas from autoregressive language modeling and trying to apply them to the mask diffusion case. So in the mask diffusion case, you have this kind of masks in any positions in the sentence, and then you have some kind of architecture that is able to both draft and verify its own draft in one forward pass of that network. And then you apply some speculative sampling procedure, and then the output of this is some number of non-factorized token predictions that you can use to infill those mask variables. And we're going to like design this architecture such that you can get all of this in like a single forward pass. So in standard mask diffusion, your single forward pass gives you some factorized predictions, but in our network, a single forward pass will give you non-factorized predictions. So yeah, there was like a couple of, I guess, main contributions to make this work. Is the first one is this like causal drafting and self-speculative architecture really requires this autoregressive kind of causal approach, because that's like how you're defining these computation parts so that you can reuse your drafting layers is kind of quite dependent on the fact that it's has this causal attention masking in it. And so we make this kind of like novel architecture that does allow you to do drafting and verification in single forward pass in the like any order mass diffusion case. And then there's also this additional complexity because we have to include non-causal blocks. So we include transformer blocks that have kind of any-to-any attention masks in them, and this results in this slight subtlety in exactly the target distribution that you're sampling from when you're doing speculative sampling. And then we have some like theoretical characterization of the target distribution that we end up sampling from. Okay, so I guess before I can go into detail of how this architecture looks like, I have to maybe set up some notation based on ordering and permutations. So I guess a lot of time mass diffusion is kind of presented as just some like xt variable that contains some number of mass tokens, some number of real tokens, and then you kind of like flip from each position. You can flip from a mask to a real token. But we're going to instead operate in this view of like any order autoregressive models, where it's this idea that you're generating kind of from some starting token to some ending token, like token by token, but you're doing it not left to right, but in some like random ordering. And it turns out like these are two equivalent views of mask diffusion. So like in this case, we've kind of have this random ordering from 1 to 9. And then say like in the first generative sampling step, you reveal like the first, the second, and the third token. And then in the next step, you reveal the fifth one and the fourth one. And you're kind of going through from 1, 2, 3, 4, 5, 6, 7, 8, 9, but that like ordering is not necessarily left to right. And then we're going to use the variable like sigma to represent this permutation of 1 to big D. So in our architecture, we have both a like drafting distribution and a target distribution. And our drafting distribution is going to be non-causal, or we're going to call it non-causal because it's going to use attention blocks that have non-causal attention masks that are like any to any, and it's going to generate us a non-factorized predictive distribution. So this is basically just the standard mask diffusion predictive distribution, where you have this like currently revealed context of tokens like 1 to little I, and you want a distribution over the currently masked positions, which is the tokens I plus 1 to big D in the ordering, and then you just generate this factorized distribution over them as this like product of kind of individual factors on all the unknown positions. And that's our drafting distribution. And then the way we write down our target distribution, and we're going to call this a causal distribution because it's going to involve the use of causal attention masks in the transformer in order to define it. So it has the same starting context of the tokens 1 to little I in the ordering. But now when you're computing this distribution over I plus 1 to big D, you have this like increasing context in your factors. So like the difference here is the context is fixed 1 to little I in the non-causal case, but in the causal case, your context is growing as you are computing each of these factors. So that's what's allowing these factors to be non-factorized. And so you have this like more powerful target distribution that you're attempting to sample from.
So the causal distribution is the same as the vanilla transformer, right? Except for the ordering, right? That it's not like autoregressive, but like random order, right?
Exactly. Yeah. So like non-causal is basically just the standard mass diffusion distribution, and then causal is the standard like LLM one, but with a sigma on it. So then, yeah, as like a schematic of what the architecture looks like is if you have this like partially corrupted sentence, as an example one is speculation is like hazarding a guess, and you have some number of those tokens being maxed out. You pass that into your non-causal transformer. So this is just like a standard mask diffusion transformer architecture with any-to-any attention masks. And then from the output of those hidden states that come out of that transformer, you kind of like just use a language model head and like linearly project that into the factorized distributions that will define the token distributions over those mask positions. So that's like kind of the standard mask diffusion kind of architecture. And then like the novel step is that we add on these like extra blocks of causal like these causal transformer blocks onto the output of the hidden states from this non-causal transformer. And then what this causal transformer is going to do is output a distribution that is this causal distribution that has this growing context. And this causal transform is going to use causal attention masking in order to generate that causal distribution. So then specifically how these like blocks are wired together is this somewhat complicated diagram that I might have to spend some time explaining exactly like why this architecture is wired like this. So if you start at the left side, where we're just looking at the standard mask diffusion style non-causal transformer, you have this like input embedding, which is just like the standard way you embed sentences, where you have an embedding for real tokens like E2, E5, E6. They're just like a word embedding for that token. And then you have a token embedding corresponding to the mask position. So that's just like a grayed out one. And then you have positional encodings, because the transformer needs some position encodings to know the ordering of the sentence. It's like we use red to represent those, pass that into the non-causal transformer. And then you get out these like hidden states, which I'm calling H. And then from these hidden states, you can like linearly project in the kind of corresponding track to a distribution over that missing position. So like the missing token in position 1, that's like 6th in this ordering. So, this is kind of arbitrary ordering that we've picked. And token 1 is 6th. So the distribution over the 6th element in the ordering is taken from this H1 hidden state. Similarly, for the 3rd token, that is 5th in the ordering. So this is the distribution over the 5th token, and then same for position 4. So that's like kind of the standard way so far. And then we apply this permutation. So this is how we're going to like use standard language model architectures, but to operate over the fact that we're doing mass diffusion in any ordering. So we permute those hidden states according to the ordering that we want to generate in. So in this case, we're doing the ordering 6, 5, 2, 4, 3, 1. It's like sigma 1 is 6, sigma 2 is 5, and so on. And then you permute the hidden states in that ordering. So you first have the H6 value, which is sigma 1, H5 value, sigma 2, H2 value, sigma 3, and so on. So I guess like the complexity that happens now is because there's this difference between how you use non-causal transformers and causal transformers to define distributions. Because with a non-causal transformer, the track corresponding to like H1 has the H1 value masked out. And so there is no leakage of information from position 1 into the track that is going to predict position 1. And so you just have track 1 predicting value for track 1, and track 3 predicting value for track 3. But in causal transformers, you have this issue where you have this causal attention mask that allows a track to attend to itself, and you don't have any mask tokens in the input to a causal transformer. You're just relying on this causal attention mask to induce the correct like conditional independencies. And so the kind of track for position for token 3, say, is predicting the distribution for token 4 because it can't predict the token position in token 3 because it's would leak information. So you have this like offset problem where you're predicting the token in the next position, even though you're in the like current position track. So like the way that looks in this any ordering kind of architecture is that, say you're in like this H2 track, that eventually you would think, in the ordering, 2 corresponds to sigma 3. So you would think this would like be the distribution over sigma 3, but instead it's the distribution over sigma 4. And then H4 is in sigma 4 position. That's the distribution over sigma 5. And then H3 is in the sigma 5 position. That's the distribution over sigma 6. So you're predicting the distribution of the next position in the ordering. And so you have to not only have the hidden state for your current value, but also the hidden state of the next value, because you need information about yourself, and you also need information about what's coming next in the sequence. So that's why we have this like concatenation of current position information and next position information. So both with the hidden states and the position encoders, you need to know like where you are now in the sequence, and you need to know what's next in the sequence. Like standard language models, they don't need this like next position information because they always generate left to right. So they always know what's coming next in the sequence. But when you have random orderings, you don't know what is coming next in the sequence. So like you have to tell it both where it is now and what its next position is. And this isn't like our idea to do this. This is like comes from a paper called like Sigma GPT, which does this like permutation of the input sequence, applies left to right, causal attention mask, and then has this kind of like current next position information in order to like produce that distribution.
So sorry, so just to summarize it a little bit. So if I understand correctly, so if we take this and map it to standard GPT architecture or just standard vanilla transformer, like encoder, decoder architecture. So here on the slide, a non-causal transformer is basically equivalent to the transformer encoder, right? So it doesn't do. And then causal transformer is kind of equivalent to vanilla transformer decoder, right?
Yeah.
So this pipeline is kind of like same as vanilla transformer up to like one exception, that the ordering is just permuted when it comes to the decoder. So first, so up to the encoder, everything is kind of the same as in the vanilla transformer. So it's just like a forward pass, but then everything is just permuted to have this ordering consistent with sigma, right?
Yeah.
And then it proceeds with standard transformer decoder, right?
Yeah, I mean, I guess the encoder is slightly different because it has mass positions that don't usually get input into the
All right.
transformer encoder, I think. But like it's basically that, yeah, like what you're saying, like you have any to any, and then you have decoding causal mask. And then we add this permutation and this like next position information. Yeah. So I guess at the output, I guess one final thing that we do is we get these hidden states coming out of the causal transformer. But in order to like make sure that this is like an easy problem for the causal transformer to learn, we like have this residual connection from the corresponding hidden state from the non-causal block. So like, the hidden state that's used for prediction of sigma 5, say H3, is just like added on to the output that is trying to predict over sigma 5. So like if the causal transformer is struggling to learn all these orderings because it's a like more difficult task than just left to right, then it can kind of default to just using what the non-causal thought, and then only when it's like figured out how to operate over all these different orderings, kind of then like learn to use this extra context that is given to it.
Sorry, so phi denotes residual connection here.
Sorry, phi.
Yes, sorry. What does phi denote?
Yeah, I guess I haven't mentioned that. So theta is the parameters of the non-causal block, and then phi is the parameters of the causal block. So like I'm using this theta and phi notation to like say this is a distribution that is defined using only the parameters of the non-causal block, and this one is using parameters from both blocks. Yeah. So yeah, I guess that was just your question there. Yeah, because this is important when we come to like looking at the target distribution from speculative sampling, but we can come back to this part.
Okay.
Yeah, so the training objective is pretty like as you would expect, where you have these two distributions coming out of your network architecture. You have the non-causal one and the causal one, and then you just train both of them with like cross entropy, maximize the likelihood over like the unseen tokens. So that's like pretty standard, and then they're both training to like the optimum of their objective is just like the data distribution, the conditional data distribution given that context. There's nothing really special here.
So here, if we just map it to vanilla transformer, so it's so here is it autoregressive. So it is still an autoregressive objective, right? That you like, but I mean up to the sigma order, right? So,
yeah, it's just an autoregressive objective. Like you have some like revealed context, like 1 to little I, and then you compute this language modeling loss over the unseen tokens I plus 1 to big D. Just in this case, your distribution is factorized, and this one it's not factorized.
So here is so if you just compare it to the original like vanilla transformer loss, so how exactly is it different?
So I guess the normal transformer loss would just look like the right-hand side. When you have like a fixed context, and then you apply your generative modeling over the I plus 1 to big D tokens. And then your left-hand side is like a standard mass diffusion loss, where you have this factorized distribution, and where you kind of just like add the two together, since we're like combining these two distributions in one network.
Oh, yeah, okay.
Cool. Yeah, so now we have our like all the pieces in order to run speculative sampling, because what we're going to do is use that non-causal distribution as the draft, make some draft tokens, and then put those tokens through the next stages of the network to get target distribution, a causal distribution, and then use speculative sampling to sample some tokens from that. So yeah, in the first stage, you do like a non-causal forward pass to get your draft tokens, and then you like in parallel. So, this is only going to be kind of like finishing the forward pass almost. You sample some tokens from the non-causal blocks, and then you finish the forward pass using those sample tokens to fill in the mass positions, run those through the causal blocks, and then you get causal probabilities on all of those draft tokens. And then you can run speculative sampling with your draft distribution being the non-causal distribution and your target distribution being the causal one. And then the output of that will be some number of tokens that are distributed according to the target distribution. And then you can kind of repeat. So if you didn't use speculative sampling, you could like run your causal blocks and then like do many forward passes of your causal blocks at the end, and then kind of like generate like an autoregressive predictive distribution. But like what we're doing here is like we're doing one forward pass, and we just kind of have a sampling stage in the middle of that forward pass in order to like the output of it is going to be tokens that are non-factorized in one go. So yeah, now moving on to like a bit more of like the theoretical analysis. We have this somewhat like issue or subtlety that's going on in our speculative sampling approach, because we have a different target distribution depending on exactly what the context was when we did the forward pass of the full network. So like if you have these two scenarios, one where you have little I reveal tokens, and then a different scenario when you have little j tokens and j is bigger than I, so you have some like a bigger context in one of the cases. Then on like the left-hand side, you pass x1 to little I through the non-causal blocks, and then I+1 to d-1 through the causal. But on the right-hand side, you pass more tokens through the non-causal block. And so like, because the non-causal block is any to any, like it knows like what that context is, and it can see how many mass tokens you have. And so if you have different numbers of mass tokens and different numbers of real context going into that non-causal block, that will change the hidden states. And so you have a different target distribution, because the target distribution uses the hidden states from the non-causal block. And you have a different target distribution depending on what the revealed context is at the time that you did that forward pass. And this isn't the case in standard speculative sampling, because you have this autoregressive causal relationship. That target distribution is kind of like unchanged as you add on more and more context. So this is like a unique like dynamic that you have in this style of model. So yeah.
Yes, sorry for interrupting. So for the standard speculative sampling, it's kind of it's proved that it always preserves the target distribution, right? And in this case, with the architecture, what you are saying is that it's like there is no theoretical guarantee that it matches, right?
It's more like you're still theoretically guaranteed to get tokens from a target distribution. It's just that that target distribution is different depending on like when you kind of sample it in the generation procedure. So it's not entirely clear when you first like write down this model what exactly is the distribution that we're sampling from. Like at the end of this generative procedure, like if the target distribution is different at each stage of the sampling procedure, like what is the output distribution for the the whole set of tokens that you get at the end of your algorithm. So the issue is that whenever you reject and you like reset and do another forward pass of your non-causal blocks, you end up with like a new target distribution. So like it feels like in order to know what that final output distribution is of your whole algorithm, you would need to like do some sum over every possible accept reject sequence in the kind of generation trajectory. And then I guess what we show is that you can actually use some like dynamic programming trick where you don't need to do this like combinatorial sum, but you can like split your likelihood over your generated tokens into like a linear number of when the rejection happens. And then you can actually like tractably calculate what your likelihood is. I don't really have time to like go into exactly the derivation of this, but I guess like summarize to show you have some like probability distribution over the output tokens from your whole procedure given some generation ordering, and then you have this like linear sum over big D number of terms, which each of these terms has this further decomposition into little d number of terms, each of which of the terms in this is computable. And then you can do this overall calculation in big D number of forward passes of your network and D squared number of operations, rather than any kind of like D factorial or kind of like power law number of calculations. So since you don't actually need to like count all of these different ways that the accept reject sequence can occur. But that's like I guess like a theoretical, more like a theoretical analysis of this kind of procedure. And as like another like corollary that you can get from this result is that you can actually like calculate a distribution over how many rejections are going to happen in your generative procedure, because in speculative sampling, you don't necessarily know how many tokens you're going to accept, like a priori. And so that, the number that you accept in each step is going to tell you how many forward passes it's going to take to generate a whole sequence. And with this kind of analysis, you can actually get a distribution about how many forward passes are going to take me to make that data point. And that's going to depend on the accept rejects ratio and things like this. But you can also calculate that quantity. Yeah, so I guess before we get to experiments, I should in the experiments we use this kind of slightly modified way of sampling in order to get a full trade-off between sampling expense and sampling quality. So the way this is modified from the previous sampling algorithm is that once you do a non-causal forward pass and you get a bunch of draft tokens, you can actually, like I was saying, you can run the causal block multiple times, but for each time you run the causal block, you can do a whole speculative sampling procedure. So you get your draft tokens from the non-causal blocks, verify those tokens with the causal ones, run the speculative sampling to accept some number of those, and then instead of rerunning the non-causal, you just decide to try again with speculative and do another forward pass for the causal blocks. And usually in our networks, the causal blocks are maybe have one causal block and then you have 11 non-causal blocks. So it's much cheaper to kind of just run your causal blocks at the end. And so you can run a few speculative sampling goes in order to try and accept more of those draft tokens. And then you can tune, how many inner loops you have in order to kind of vary this kind of number of forward passes to sampling quality trade-off that we can look into in the experiments. Okay, so yeah, I guess starting off, we just looked at some simple text data sets, like this text date character level modeling problem. And yeah, I guess one interesting thing that you can start to look at when you start training these models is that you have this very clear point at which your causal distribution improves upon the non-causal distribution. So if you're just looking at the training losses, you have these two distributions, they both have a loss on the data set. You have this initial stage where these two distributions are kind of locked together and they're both kind of predicting the same distribution because of that residual connection. And then at some point, the causal blocks start to learn to use the extra context that is available to them. And then you have this dramatic decrease in loss as they're able to better model the data distribution using the causal attention mass that they're given. And then this is kind of exciting because I guess when you sample just with standard mass diffusion, this level of loss is the upper bound of what your model is capable of, because this is the power with which that factorized distribution can model the data distribution. But then, and this drop in loss is that is actually signifying the benefit of being non-factorized, because it is able to better model the data distribution. And so, now we are able to sample from this non-factorized distribution, we are able to get that kind of reduction in loss and that actually power to model the data distribution. And we can kind of unlock that with the speculative sampling approach. So in terms of actually, sorry, yeah.
Sorry, what exactly do you mean by extra context here?
Extra context?
Yeah, so here
yeah, so it's I guess, if half of the sentence is revealed to the non-causal blocks and the rest is masked, that's all that the non-causal blocks get. But then when you get to the causal blocks, because it has this increasing kind of conditioning information, because it's an autoregressive distribution, for the final token, it is able to see every other token that was that is in that sentence. But for the non-causal blocks, when it's trying to predict the final token, everything else is still masked. It doesn't get any extra information to predict that final token. But the causal distribution, because it's autoregressive and it has this gradually increasing context, it is able to see all the other tokens that the non-causal block didn't see. And so it can use that information to make a better prediction over that final token.
Yeah, okay, I see.
Yeah, so when you actually sample the model, we were measuring like in this like toy data set, you can just measure like spelling accuracy because it's tokenized at a character level. And then you can see how the spelling accuracy like trades off with number of forward passes in your generation trajectory. And then you can see that like, down to these like lower levels of number of forward passes, you have this like almost like 2 times improvement in like a reduction in forward passes for a given level of sampling quality, because it's, has this more powerful predictive distribution that it can sample from. And then we also tried like GPT-2 scale modeling, which is just on like the open web text data set. And this one actually has like a proper tokenizer with like 50,000 tokens, just using like the GPT-2 tokenizer. And then I guess we can't measure like spelling accuracy. So I guess one metric that people use in this kind of benchmark is you take like a pre-trained language model, just like a standard autoregressive model, and you compute its log likelihood on your generated sentences. And then if it has like high likelihood, and like if the pre-trained model likes your sentence almost, then you assume that it's a good sentence, which has some downsides where if you kind of like have a mode collapse issue, then like if you're just repeating the same token over and over again, like an autoregressive model will really like that sentence and assign it a high likelihood, but you have this like mode collapse problem. So when you do this kind of metric, you also have to measure the entropy of your generated distribution. So like you're not just sampling the same token over and over again. You have this entropy over your distribution of tokens that you're sampling. And as long as your kind of entropy is high and matching the data entropy and your generative complexity is good, then you can assume that you've made like a good sample. Yeah, just the entropy thing. So yeah, comparing to like mass diffusion, if we just like, first like entropy at these different numbers of forward passes, we have like pretty similar entropy values as mass diffusion. So we're not like mode collapsing or anything like that, other than mass diffusion would do. But in terms of negative log likelihood, where lower is better, we're getting this like, our value at 32 forward passes is the same as the mass diffusion value at 64 passes, and our value at 64 is the same as the value at 128 for mass diffusion. So again, we're seeing this like 2 times reduction in forward passes required for a given level of sample quality. When we compared to this approach to this other approach to like speeding up mass diffusion models, where you have this like teacher-student distillation style training. We have like a mass diffusion model with many samples, many steps in your generation trajectory, and you try and distill that into one that's taking only fewer steps. Where you see it gets like incredibly low negative log likelihood, but it's also like low entropy as well. So it's like it seems that that style of speeding up the sampling seems to like more kind of mode collapse than our approach that stays the same kind of level of diversity as the mass diffusion model. And then we also ran some interesting architecture ablations where the first one is, if you remember, I mentioned this residual connection between the non-causal hidden state and the causal hidden state. And if you remove that residual connection, then you end up with this worse quality to sampling time trade-off, which could be related to different reasons, maybe like one of them being that the draft and the target distribution, the more they're aligned, then the more they can agree on like what tokens are good, and the more tokens you're going to accept from your speculative sampling procedure. So if you remove that residual connection, then they're going to like become misaligned more, and then you have like a reduction in your acceptance rate. So that's kind of like worse in your algorithm. And then in our final architecture, we use 11 non-causal blocks and just 1 causal block. So, just adding a single kind of like causal head almost onto a mass diffusion model. And that seems to work the best. So like if we instead have 10 non-causal blocks and 2 causal blocks and try and like maybe make the target distribution a bit more powerful, make the draft distribution a bit weaker, this actually is worse than just having, a very powerful draft and like a single causal distribution on causal head on the top. And what I think this means is that like these hidden states that are coming out of the non-causal block, they're like so powerful that like just a tiny amount of causal information is enough to like convert those into like powerful causal like hidden states that define a good causal distribution. And yeah, I just think that was kind of like an interesting ablation that wasn't necessarily like what I expected. Yeah, and then I guess the final experiment that we did was on like protein sequence modeling, where we just took the ESM2 model, which is just like a 32 block transformer model trained on 40 million amino acid sequences. And this time, to measure sample quality, you take a sequence sample from your model and you run it through a folding model. And this one, I think it was an ESM fold or omega fold. And then you calculate a confidence metric on like how confident the model is that that sequence would fold into this structure. Yeah, and so like a high PLDDT value is indicative of like, it's a good quality sequence because it's quite confident that it would actually fold up into a structure. So like this is like an example, like on the left you have a sequence with low PLDDT, and when you try and fold it, it's kind of it's not like very consistent structure. But with a high PLDDT sequence, when you fold it up, it kind of has all this secondary and tertiary structure that it's indicative of being a high quality sequence. And then when we compare to like mass diffusion here, we just take the ESM model, add on a single head, we freeze all the weights of ESM2, and we just fine tune this causal head. So we can kind of like squeeze out this extra performance from ESM2 by training this causal distribution, and then we're able to improve our like PLDDT to number of sampling steps trade-off here versus the mass diffusion model. Okay, yeah, that's the end of my slides. So if anyone has any questions, I'll be happy to take those.
Yes, thank you very much, Andrew. It was a great talk. So maybe I have a question.
Yeah.
So it looks like an exciting progress for improving discrete diffusion, like in general. And I have a general question. I know. So what is the state of the art for discrete diffusion versus just autoregressive modeling? So I know that there are some recent like papers showing like there is like high potential, but I'm still not sure if it actually outperforms, or like at least on some tasks, if discrete diffusion outperforms autoregressive style modeling, or like what's like the current state of it.
Yeah, I guess like I think definitely on text it doesn't outperform standard language modeling. I think it's more on these specific like reasoning tasks that discrete diffusion models seem to show like more promise, like coding or like mathematical reasoning, where I guess you very much don't have this like left to right kind of indicative structure. Like I think if you're just going to do normal language modeling, it doesn't really make that much sense to use discrete diffusion because it's having to like generate sentences in these kind of somewhat arbitrary orderings that are not very like natural for generating standard sentences. But like for something like coding, where you really do have this like back and forth kind of reasoning. And also with like mass diffusion models, you get these like extra kind of sampling algorithms you can use with kind of correction steps and picking orderings, picking like which like positions to resample, things like this. I think people are able to like squeeze better performance out on those specific tasks. But yeah, I'm not like fully aware of like numbers of which one is on which task that's kind of like shown to be better now. But I think these are the ones that most people are like excited about at this point.
It also seems to be very excited in the case of proteins, because there is like this order and like this from left to right. Also, then is probably not that like significant for like machine learning. So it seems
Yeah,
to be
it
very...
definitely seems to be the standard in protein sequence modeling as well. For sure.
Yeah, I don't see any questions in the chat. So maybe...
Cool.
Maybe maybe then I will ask one more question. So you combine this causal and like non-causal modules into the same architecture. Is there any benefit? Because if I remember correctly, in the standard speculative decoding, they use two models, like smaller model to suggest a draft, and then like a bigger model, target model, right? Like what is the main like intuition, or what is the like main advantage of combining it under the same under a single model?
Yeah, I guess you get like deployment simplicity because you just have one network that you have to kind of support. And like I guess you're like when you're running in production, it's probably easier to to have just like one network that's outputting these two distributions than having to maintain two separate networks. You also get this like benefit of kind of like synchronization between the target and the draft model, because they're like the same weights, so they tend to like agree more on kind of what are good tokens, and both assign high probability, which is good. I guess an interesting thing in our architecture is that like normally in speculative decoding you have a small draft and a big target, but here it's almost like a big draft and then an ever so slightly bigger target. But like it's kind of interesting that works, because it seems that like you have such a good initialization of the hidden states that like you just need a little bit of extra stuff with the extra tokens revealed to turn that into like a way better distribution. So it's actually, I guess, slightly different than the standard speculative decoding kind of setup.
Yeah, it was interesting to see the ablation you showed. It was like kind of unexpected.
Yeah.
So maybe if anyone on Zoom has any questions, please feel free to ask. So it seems there are no questions. So thank you very much, Andrew, again. It was a great
Thank
talk.
you. All right. Thank you for the questions. All right.
Yeah, have a nice day.
Yeah, see you.